Hello YouTube, buckle up. Today's a long one because I've decided that 5 example problems are important. So we're going to be talking about angular kinematics. In particular, we'll be talking about sort of the differences and similarities between how you can treat things when they're spinning versus how you treat things when they're just moving in a line, so linearly. Ideally, end of the day, you should be able to talk about the differences between the angular and the kinematic variables and how to get between them. And that's sort of the really big thing. Also, if you can relate circular motion from way back when into the angular variables, you're in a great spot. So, radians. Turns out stuff can spin. And when you have an object that's spinning, let's say it starts out here. If it pivots around a point, it'll rotate a certain amount. And we need a way to measure how much it's rotated. Now, normally people used to measuring something like that with degrees, but for the math that we're going to be doing, it'll only work if it's unitless. And the only unitless measurement for degrees are radians, so we will be using radians. Because this is a calc-based class, I'm going to kind of hope that you basically know what those are already, but it is the fraction of the circumference that you've already traveled, where 2 pi radians is one complete fraction of the entire circumference. Personally, remembering it that way is really helpful for figuring out how to translate between linear and angular later down the line. So when you're doing your angular variables, okay, that was weird. When you're doing your angular variables, a lot of the things are the same. So angular position is the amount that the object has rotated from a fixed reference. So like this is your 0 point, it's rotated pi radians from that reference point. It's rotated 2/3 pi radians from that reference point. Your angular displacement is the amount that it's rotated from the point that you set as 0. So just like how displacement is your distance and direction from where you start to where you end. Angular displacement will also be the distance and direction of rotation from one place to another. Angular velocity will be the amount of radians you rotate each second, and angular acceleration will be the amount that your angular velocity changes by each second in radians per second squared, which these units get weird on both of these because radians are unitless. So it keeps doing this. That's actually really annoying. I think the thing is set to have an auto timer. Oh well. So yeah, that's pretty much going to be it for those two. The direction of these things is weird. The right-hand rule is how you would figure it out. The problem is that the camera's flipped here, and it's not really gonna matter until we get to torque. So for now, we can use clockwise and counterclockwise. The problem with clockwise and counterclockwise is that the same object, when looked at from 2 different sides, will be rotating clockwise when looked at from one side. And if you bring your head around to the other side, it'll be going counterclockwise. So this would be for me going clockwise. And if I bring it around to this side, it'll now, from my perspective, be going counterclockwise. And the auto timer. So talking about how to translate between those things, let's go from linear to angular and back. Oops, there we go. So when we're going from linear to angular, the easiest one for me to remember is thinking about how to get the circumference of a circle. Because if I want to get the circumference of a circle, let's say I've got this stick, and I can think about that stick as a radius that's sweeping out a distance that is the circumference of a circle. Well, that distance is going to be my radius times 2 pi. So 2 pi r will get me the entire distance. Well, 2 pi is a full circle. So if I only go by pi over 2 radians, then I will only have 1/4 of that circle. Well, because the whole circle is 2 pi, pi over 2 times my radius will give me this arc length in here, that will represent 1/4 of the circle, the letter for which is S. So what's neat about this is that that always works. So if I take my angular and I multiply it by the radius, that will give me my linear equivalent. So the tangential distance you've traveled to the circle you're going, or the arc length of the circle you're mapping out while something is spinning, will always be equal to the radius of the thing times the angle that it swept out in radians. Something that's going to be consistently annoying about this that you really have to be careful of keeping track of. This part is the same everywhere on the object. This one gets bigger. As you travel away from the pivot. Because the distance from here to here is much, much, much greater than the distance from here to here. Look at the amount of pen ink that those two things use differently. The closer you are into the center of a pivot, the less distance you'll travel. And for me, again, an easy way to remember that is to go from here to here and be like, okay, well, that was 90 degrees. And if I put my finger here, it was still 90 degrees, but the distance my finger travels is much smaller than if my finger is out here. I have to push much greater distance. So the linear distance that an object rotates, or a point on an object travels, will vary based on how far away it is from the pivot. But the angular position and the angular displacement will not. Those will be consistent throughout the object. And that's something that you want to keep track of. And so if you've got a spinning object, the angular displacement in a given second will be the same across any amount of time, no matter where something is on that object, assuming it's a rigid object, meaning it doesn't wibble wobble and spin at different rates depending on which part of it is. Like if you stirred soup, soup wouldn't be treated as a rigid object. Different parts of it will spin at different rates. But if you spin like a record or a CD or a frisbee, those will all be things that are spinning at a fixed rate for the whole object. So if that's happening, your angle will be the same everywhere. Now, if we take this and we take the derivative with respect to time, where the object is compared to the pivot is not changing. That's constant. So the change in your angle with respect to time is where the variables start getting weird. Will give you your angular velocity, which also multiplied by your radius will equal your tangential velocity. And if you do it again, your angular acceleration times your radius will equal your tangential acceleration. This is one you've got to be careful of. Tangential velocity is the one that we used when we were doing circular motion. Centripetal acceleration, the acceleration towards the center, is the one we were using when we were doing circular motion. The tangential acceleration was something that we were only measuring with stuff like kinematics. We did not have a decent equation for it before. And that's actually something that we're going to need to be careful of, is that as we're going through these things, your tangential acceleration is separate from your centripetal acceleration, and you have to be careful that you're using the one that you think you are. So writing down the new variables real quick, omega is your angular velocity, which is measured in radians, which are unitless per second. Per second is hertz, so you could just measure this thing in hertz, which is a little bit weird because that's normally used to measure frequencies. There's a relationship there. And alpha is your angular acceleration. And that one is in hertz squared, or 1/seconds squared. Cool. So those are your relationships translating between those two things. The next thing to talk about is the angular kinematics equations. Turns out they should look pretty familiar, actually. Your final angular velocity will be equal to your initial angular velocity plus your angular acceleration times time. Your angular displacement will be equal to your initial angular velocity times time plus 1/2 your angular acceleration times time squared, because they're all by the same relationships. We can just take an integral of a constant acceleration and get, well, a constant angular velocity and a constant angular, with a constant angular acceleration. And so all your relationships where you were like, okay, I can take a derivative of an acceleration equation, that'll give me a velocity equation. Nope, other way around, sorry. Derivative of a velocity equation, that'll give me an acceleration equation. I can do integrals of velocity equations to get position equations. Works here too, it's just going to be for the angular equivalence, which is honestly quite nice. All your old rules too about finding maximum and minimum, like local maxima, local minima, still hold. The last thing is an interesting relationship between your centripetal acceleration and your angular velocity. So because your angular velocity is related to your tangential velocity, and we'll derive this in a sec, your centripetal acceleration will be related to your tangential velocity. Now careful, that's not related to your tangential acceleration. So your tangential acceleration is what's going to determine how much the object speeds up or slows down as it goes in a circle. The centripetal acceleration is going to be the one that's necessary to keep it going in a circle. So centripetal acceleration, always on. Tangential acceleration, how much it speeds up or slows down by. And honestly, I should write that, so I will. And we should drive this equation. So we will. So your tangential acceleration is amount sped up / slow down. So this is the one that controls speed, and it's the one that's related to alpha. Your centripetal acceleration is how much you need to pull in to turn. So this is the one that deals with speed control. This is the one that deals with turning. And that one's going to be related to your velocity, weirdly enough, not your angular acceleration. And to get a quick derivation of the equation that we just had up on the board, your centripetal acceleration is going to be v squared tangential velocity squared over r. But tangential velocity is equal to omega times r. All of that's getting squared. I don't know why I did the extra parentheses. So omega squared r squared over r gives you out r omega squared, and that's your relationship between centripetal acceleration and angular velocity, which can be super useful. So, starting our 5 whole example problems. And I will almost definitely, as I'm switching back and forth here, inevitably wind up, there's a little bit of, there it is, there's a little something under the sheet that was getting in the way. I will almost definitely wind up leaving it on the wrong screen for a bit. Sorry about that. I don't know why it's also swapping back and forth between the wrong things. That's kind of annoying. But we'll see how it goes, and it is what it is. Okay. So, 2 children are sitting on a merry-go-round with a radius of 4 meters. Child A is at the end and child B is at the halfway point. It completes 20 rotations in a minute at a constant velocity. What is the angular velocity of each child? So we've got 4 meters. B is 2 meters away. And we've got 20 rotations in 1 minute. A is find omega. B is find tangential velocity. C is find alpha. And D is find the net force. Great. Let's solve. So to figure out omega, this one's actually mostly going to be unit conversions. Currently, we have the number of rotations per minute. Omega typically should be in radians per minute, or radians per second is the more consistent one. So to do a conversion, we haven't really done much of factor label method, but we're going to do it now. We've got 20 rotations in 1 minute. But I don't want rotations, I want radians. So for me, a really good way to do that is to say I need to cancel out rotations. And if I multiply by something that's the same on the top and the bottom, as in the size of the top and the bottom are the same, then I've multiplied by 1. So I haven't changed my size of my term. All I've done is I've changed how I'm thinking about it or how I'm writing it. In this case, we would have 1 rotation gives me 2 pi radians, which are unitless. So this would get me into radians because I would be getting out of rotations and into radians. But I want per second. Now minute is on the bottom of the fraction right now. If I want to cancel out minute, I'll need to put minute on the top. 1 minute is equal to 60 seconds. So if I multiply with minutes on the top and seconds on the bottom, I haven't changed the size of the thing, I've only changed the units. And this, for me, is really useful as a tool to make sure that I don't accidentally multiply by something I should have divided by or divide by something I should have multiplied by, especially when you get to things like minutes squared or squared centimeters that you need to convert into meters. It helps you remember to do the right number of multiplications or divisions. And so this method tends to be really good. Again, quick breakdown of what I did. Put the units you want to get rid of on the opposite side of the fraction. So in this case, for rotations, it was on the bottom. For minutes, it was on the top. Represent the fraction that you're multiplying by as something where 2 sides are equal. 2 pi radians is 1 rotation. 1 minute is 60 seconds. The other side should be the other thing it's equal to, frequently, and if you can, what you're trying to get into. So getting rid of rotations, turning into radians. Getting rid of minutes, turning into seconds. And then what you should be left with are units that are the correct things on either side. So in this case, we've got 20 over 60, which is 1 over 3. We've got 2 pi. So 2 pi over 3 radians per second. And I don't actually have to write the radians because, again, they're unitless, but it helps me remember what things are. So this is our angular velocity, and this is our angular velocity for the merry-go-round. Now, the kids are on the merry-go-round. And because as the merry-go-round rotates, if the merry-go-round does 1 full rotation, it doesn't matter if it's the inside or the outside. 1 rotation for the merry-go-round will be 1 rotation for both children. So that part is the same for both. However, when we get to B, in order to do 1 full rotation, child A will travel a much greater distance than child B does. So child A on the outside of the merry-go-round will have the same angular velocity, it'll go the same number of radians every second, but it'll have a much greater linear velocity because it goes a much greater linear distance in a given second. So to figure that out, all we have to do is take omega, multiply by r, and that'll give us our tangential velocity, which in this case will be for child A, 2 pi over 3 times 4, so 8 pi over 3 meters per second. And for child B, it's going to be very similar, except we're going to have 2 pi over 3 because they have the same angular velocity times the different radius of 2, which gives us 4 pi over 3. So because it is half as far in, it goes half the distance in a given second and half the linear distance for a given rotation. Cool. Alpha is actually really easy. The angular acceleration of this is that it was going at a constant velocity. It's not speeding up or slowing down. So angular acceleration is 0. Now, that said, and that'll be true for both of them, And if they were accelerating, the acceleration would be the same for both of them, unless one was like walking forward on the merry-go-round compared to the other one. For C, this is where it gets a little weirder though, because this is related to your tangential acceleration. So they're not speeding up in terms of like their forward or their backwards motion, but they have to get pulled in towards the center of the merry-go-round or they wouldn't turn and they would just keep going in a straight line off of the merry-go-round. That's not happening, so something has to be pulling them in. That'll be their centripetal acceleration. Well, thankfully, centripetal acceleration will be equal to omega squared r. If I multiply that by mass on both sides, that'll give me my net force, because mass times acceleration will give me my net force centripetally. Because they're not accelerating linearly, or sorry, they're not accelerating tangentially, we don't have to care about that part of 0. This is their net force. And we've got numbers for all of these things, except we don't know the mass of each child. So I can get their centripetal acceleration, I can't get their net force. So this is what it would be in terms of omega, r, and m, which we have for each child. They'll be different for each child because they have a different omega for each child, as we found earlier. That's not true. They have a different r for each child. So compared to each other, what we can say is that this part's the same, this part's the same, A is double B. So we can say that the net force on A is double the net force on B if mass A equals mass B. But we would have needed the mass to actually get numbers for this problem, which was my bad. All right. Next one. A wheel is spinning at 4/pi revolutions per second when it begins to accelerate at -2 radians per second squared. So once again, we've got to deal with our units. What is the maximum angular displacement for the wheel? How far would it travel in that time? And how long would it be before the wheel returned to its start position? I'm going to kind of use this mostly as a way to showcase a bunch of the old kinematics tricks and how they're still applicable. You could do much more robust ways of solving a lot of these, but this is what I'm going to go with. So we've got our wheel. We've got that our initial velocity is 4/pi revolutions per second. Going ahead and doing a quick conversion. Using the same method as before, we'll need to multiply by 2pi to get out of revolutions. So omega naught is equal to 8pi/pi, which is 8 radians per second. So now I've got my omega again, something useful. And we are being asked about it when its angular acceleration is a constant -2 radians per second squared. Okay, solving this one out. For A, we are looking for the maximum angular displacement in the positive direction. Well, maximum displacement occurs when the velocity is 0 because those will be the points where it turns around. Same as before. So what I can do is I can set up, my final velocity will need to be 0. My initial velocity is given as 8. My angular acceleration is given as -2, and I'm looking for my theta. An equation that relates all of these is that my final angular velocity will equal my initial squared plus 2 times my angular acceleration times my angular displacement. This one's 0, so I don't have to care about the fact that I forgot the squared. Oops. Subtract off my initial angular velocity squared, subtract off my initial angular velocity squared. Just diving into solving real quick. That'll give us 2 alpha times our angular displacement. Divide by 2 times our angular acceleration, divide by 2 times our angular acceleration, and that'll land us with -8 squared divided by 2 times -2, which will give me that we rotate a distance of 64/4, so 16 radians in that time frame. Did I accidentally solve for B instead of A? No. But I did accidentally ask for the same thing in A and B. I think A was supposed to be how long would it take to reach its maximum angular displacement, and B was supposed to be how far would it go. Either way, we can just pop it into another kinematics equation to get the time, which I do want to demonstrate. So we've got omega equals omega naught plus alpha times time. This one's 0 minus omega naught, negative omega naught will equal alpha times time, divide by our alpha. We'll get -8/-2 equals 4 seconds as our time. So it takes 4 seconds to stop and goes 16 radians in the process. For C, we're being asked about how long would it take to return to its starting position. This one is, I suppose, a little ambiguous because every 2 pi radians will bring it back to its original position. I'm going to assume that it means an angular displacement of 0. Maybe it's something where it matters how far it's actually rotated and the actual position compared to its start point matters. Something that can come up for these problems, though, that you should watch for is if the question's asking you how long will it be before a rotating object gets back to its original orientation. And that would be when it goes a rotation of 2 pi. But for C, are sort of a couple ways to approach it here. If we think about the way that this would look when graphed, it's a little easier to see that if we look at velocity versus time, we're looking for a place where our positive displacement has gone the same amount as our negative displacement. And so we'll get 2 similar triangles crossing through the 0 point, where this is the time for the first half, and this is the time for the second half. And via symmetry, in order to get the top half and the bottom half to have the same area, well, they've got to have the same amount of time because the slope is constant. So our time will just be double the original time. Alternately, we could solve it by saying that our positive velocity at the initial will be equal to our negative, the negative of our velocity at the end. Another way we could do it is solve it with our displacement being 0 for angular displacement. I'm just going to go with it's double the time because we've got 3 more examples to get through and they're all harder than this. So I'm just going to do 4 seconds times 2 is 8 seconds and call it a day. But any of the conceptual tricks that worked for the linear stuff still work here because it's all the same equations. You've just got different fancy Greek letters instead of the letters you're probably a little bit more used to. Okay, example 3. Motor spins at 200 revolutions per minute when it begins to accelerate at -2 radians per second. This is the same problem. Okay, I think that one of the screens is updating and one of them isn't, which is annoying. A motor spins at 200 revolutions per minute. There are 2 gears, 1A of radius 0.1 and 1B of radius 0.2. One gear is attached to the motor and one is attached to the wheel. How far would a cartwheel move in a minute if A was the one attached to the motor and B sort of was functioning as the wheel? And then B is flip it. So, getting everything written down once again. We've got that our motor is 200 revolutions per minute, which, just quickly converting again, is 400 pi radians per minute, which is 20 pi divided by 60 over 3 radians per second. Although actually, we're being asked about how the wheel moves in a minute. I'm gonna leave this in per minute, because then I just have to multiply by 1 and I will get my answer. There are 2 gears, 1A with a radius of 1 meter, 0.1 meters, and B with a radius of 0.2 meters. Cool. So the trick for this, and a lot, and A is where A is attached to the motor. B is the flip, where omega B is 400 pi radians per minute. And then A is hooked up to it after that. This one's B. Okay. Cool. Let's do it. So, for A, we have the angular velocity of A, and we're looking for the angular velocity of B. Now, the trick is that when you have a gear in contact with another gear, if they're rolling through each other without slipping, gear A will travel a linear distance that is the same as gear B, because the distance that each of them goes needs to be the same when you're just looking at it. But the same linear distance at a different radius away from their pivot points will create a very different angular displacement. So, unlike objects where you've got one person on one object, when you have 2 gears attached to each other, it's the flip. Instead of having the same linear angular displacements and different linear displacements, gears will have the same angular displacement. Nope, the same linear displacement, but 2 different angular displacements. So the distance traveled by A is going to equal the distance traveled by B. And we can say that the distance traveled by A is going to be the angular velocity of A times the radius of A, whereas the distance traveled by B, which is the same, is going to be the angular velocity for B times the radius for B, because of our relationship between angular and linear. By this point, we just have everything for the problem. So to figure out when we've got A with a known angular radius, we divide by RB, and we divide by RA for the other one. But we do need to know that trick to get this to work. So if you're using the trick, if you're careful with your algebra, if you're writing it out, not too bad. If you're not using the trick, next to impossible. Got 200 pi, 400 pi, there we go, times our radius of 0.2 divided by our and actually, you know what? I just realized this is going to get us our displacement. We're asked for the linear distance the wheel travels. It's the same linear distance, so I was just about to divide by the radius and then re-multiply by the radius for B. We don't have to do that. Although this will get us the linear velocity. Sorry about that. If the distances they each travel in a given amount of time are the same, then the velocities they each travel in a given amount of time will also be the same. So this will give us our velocity. Saving out a quick shortcut. But something that I do want to highlight here is that the distance that the first wheel travels, or the radius of the first wheel, the two velocities divided by each other will be the inverse of the two radiuses. So the smaller gear will rotate at a much higher angular speed, whereas the bigger gear will rotate at a much lower angular speed, but their linear speeds will be the same as each other. Yes. Yes. So when we hook the motor up to the smaller gear, we'll get out a linear speed of 0.2, so 80 pi, and then that'll be radians per minute. If we want to get from, that's the linear speed, meters per minute. If we want to get it into meters, we'll just have to multiply it by a minute, so 80 pi meters. For B, it'll be the same, but we want to use the stuff for B. So we'll again get 400 pi times our 0.1. That'll give us out 40 pi meters per minute. And when we hook it up to the larger gear, it will go 1/2 the distance in the same amount of time. The trade-off for this is because of how torque relationships work, which we'll get to eventually. You have double the drive power when you do it this way, whereas with the other one, when you hook up the motor to the smaller gear and then hook it up to a bigger gear, when you hook up, I flipped the two gears. I did 0.2 for the 0.1, 0.2, thought that looked wrong, 40, 80, 80, 40. Jeez Louise. Okay. So when you hook up the motor to the bigger gear and then connect that to a smaller gear, you won't go as far. You'll go much less far, but you will have a lot more power behind it, which we'll learn about why later. When you do it the other way around, you'll have a lot less power behind what you're doing for the spinning, but you'll go a lot further and a lot faster. Cool. 2 left. Person is riding a Ferris wheel with a radius of 20 meters and notices that it takes 2 minutes to complete a revolution. So we've got our Ferris wheel, our radius is 20 meters. We've got a 60 kilogram person, and our angular velocity is 2 revs, oh no, half a revolution per minute because it takes 2 minutes to complete 1 revolution, which is equal to pi radians per minute, or pi over 60 radians per second. We will have to get it in radians per second for this one in order for the force metrics to work out. How much is the normal force on the person at the top of the ride? So, our good old friend free body diagram returns. We'll have our normal force going up. We'll have our force of gravity going down. The net centripetal force here will be equal to the force of gravity going down plus the normal force going up. This is our only real relationship I can think of with normal force, which is why I've picked it. Additionally, our net centripetal force will need to equal omega squared times r. Well, cool, we know r, we know omega, our only variable here is Fn. So add mg to both sides, times m, add mg to both sides, and we'll get that our normal force will be equal to omega squared times rm for our acceleration times our mass, because net force equals mass times acceleration still, hasn't gone away, plus our force of gravity. I just realized this net centripetal force needs to be towards the middle. Gravity is going towards the middle, so I'm going to make it positive. Normal force is going away from the middle, so I'm going to make it negative. This should be negative. This should be negative. This should be negative. I realized that the taking the total force shouldn't be getting bigger with more gravity. It should be getting, normal force should be getting smaller with more gravity, because then the more gravity we have pulling in towards the middle, the less normal force we need to cancel it out to get it so that we've got the right amount of force going down. So this is minus mg, which, throwing all our numbers at it, we've got pi over 60. Oh, I did not mean to do this at all. Squared times our radius of 20 times our mass of 60 minus 600. No, did I still send the person flying off the Ferris wheel? I think I still made it too fast and the person goes flying off the Ferris wheel. No, we should be good, sorry. So we've got pi squared, which is about 10, but I will write it as pi squared, times 20 times 60 over 60 squared. One of the 60s drops. No, I have done it. Whoops, I have launched this poor person, because right now we've got a negative normal force of quite a bit. So I accidentally made the person going way too fast. Ferris wheels shouldn't complete one rotation every 2 minutes, I guess. Pi over 60. That, or I had my signs right the first time? No. Yeah, I launched the person. I should have made the Ferris wheel spinning slower. That's a little bit weird to me, because needing I did get the signs wrong. No, this is fine. Yeah, something about this is feeling a little off. I'm not sure what, but math checks out. Our basic idea is we've got our centripetal force. Our centripetal force is going to be gravity going towards the middle, so it needs to be the same sign as our acceleration. We've got normal force pushing away from the middle, so it should have the opposite sign as our acceleration. Oh, there we go. This was negative. We fixed it. We have not launched them. Friction, normal force was supposed to be negative. I did, in fact, do it slowly enough. Jeez. So we'll get about 600 if we cancel out the negatives, minus pi squared over 3 as our normal force, which is roughly 600 minus 10/3. So take that as you will. Okay, last one. A child has a coefficient of friction of 0.6 with a merry-go-round. If the ride starts from rest and is accelerating at 1 hertz squared, how long will it be before the child starts to slide off the ride? So for this one, our big thing is that if the amount of friction we need to keep this kid going towards the center, which will be our centripetal force, if that gets bigger than the amount of friction that's available, which is the maximum amount of static friction, then the kid will go flying. So, to figure this out, my guess is the distance that the kid is from the center of the merry-go-round is going to matter, and I should have actually provided that, but let's double check. We know that our net centripetal force on our kid is going to be equal to our force of friction, and that will also be equal to the maximum static friction. And that'll also be equal to the mass of the kid times r omega squared. Now, going back and going to our force of friction, we know that our force of friction will be equal to mu mg, because we've done a whole lot of problems like this before, and that'll be equal to m r omega squared. Thankfully, mass drops. Dividing each side by r, we'll get that mu g over r is going to equal omega squared. So now we know the maximum allowable speed that we can get this thing to go. Angular speed. Well, thankfully, if we're looking for time, omega is just going to equal omega naught, 0, plus angular acceleration, which we know times our time. So divide that bad boy by our angular acceleration, and we'll have our answer. 1 over our angular acceleration times the square root of mu g over r will equal our time. So we do need to know the radius. Basically, if the kid is really far to the outside of the thing, this does go down with square root, so it's not quite linear. I got so close. I made it to problem 5 before I solved the problem without changing views. I'm so sorry. So close. Re-going through it. The more friction we have, the less the kid's going to slip and slide. Now, the amount of friction is going to determine whether or not the kid gets enough centripetal acceleration to start sliding out, to stop them from sliding out. When that is at their maximum value, which happens when you've got mu mg, because their normal force is going to be balanced out with their gravity, that'll need to equal mr omega squared, because r omega squared is going to be their centripetal acceleration, and m is their mass. So mass times acceleration gives us force. This g should not have been here. Dividing each side by r and square rooting, and mass as well, will get us that mu g over r square rooted will equal our omega. Now, because it's going at a constant angular acceleration, we know that omega is equal to omega naught plus alpha times our time. Dividing each side by our angular acceleration will tell us that if we find omega and divide it by our angular acceleration, find omega and divide it by our angular acceleration, then that'll give us our time. So, throwing numbers at it, I would need to have given the radius. Relevant for this one, basically looking at it, our time is inversely related to the radius. So the tighter in they are, the more centripetal force they'll need. And if the tighter in they are, the more centripetal force they need, then the bigger the radius is, Yes, so the tighter in they are, then the less, the tighter a turn they're making. But the tighter in they are, the shorter a distance they're traveling. And those two things are competing. The closer you are to the center, the less distance you have to go around in one go around. But the further you are from the center, which is good. If you go a small distance in a turnaround, you're progressively going slower. So going slower means you need less force. The further away you are, though, the wider a turn you're making, and making a wider turn is easier than making a tighter turn. So it's these two things competing. The fact that they're taking a wide turn on the outside is competing with the fact that they're going much faster on the outside because it's a constant angular acceleration, but the linear velocities are, and a linear velocity is, angular velocity as well, but the linear velocities are increasing the further out you go. So those two things are competing basically because v gets squared and omega gets squared. The further out we are, the less time it'll take for the kid to start flying off. And you can feel this if you've ever been on like a spinny ride. If you stand in the middle, it's much easier not to get pushed out to the side than if you stand on the edges. You get sent off flying. So that's our answer. Throw numbers at it. Remember to put the radius in the problem if you're giving this as a problem to other people. Thank you so much for bearing with me. 50 minutes is too long. Goodbye, YouTube.